All right. Today's going to be a short stream. I think it'll be interesting, though. All right. So, sometimes when a bug is super duper hard to find, it means there was never a bug. And I think that might be the case now. So I didn't do any debugging, any coding since we last met. Just let my mind stew on it. I think I found out some interesting things. We're about to find out if I was right. Okay. This is image 0, right? So what is GDC of image 0? Oh, right. What is GDC of MFS of image 0? 0.1381. Let's keep this number in mind, okay? Now, what's the bound of compressed sensing? Three times 10 to the negative 6, but this, of course, is... Okay, yeah. So, the compressed sensing problem is infeasible. Because even when we just try to solve the linear system in a way that satisfies the constraint at all, we get a number that's way, way, way too large. Oh, 10 to the 5 too large. 10 to the 5. So when we multiply the constraint by 10 to the 5, the bound on the constraint by 10 to the 5, then only then do we start using the compressed sensing objective function. Okay, so the code's working as intended. Is the bounding correct? Well, let's stop doing these checks. I don't think so. Because when we estimated the bound this way, or when we just used var variance, the MATLAB's variance function, then it got, about the same number. So that's not the issue either. I don't think. So what's the issue? Well, let's go down to this image 0 here. This MFS is an overdetermined linear system. Compressed sensing is supposed to fill in what's underdetermined. So what to do? What was image 0 before I did that warm starting thing? Just zeros. Oh, I see. Okay, so I think the thing to do, here's how I'm going to code this up right now. If compressed sensing is equal to true, we're going to do this. Then we're going to check. Well, where's the bound? Warning. The compressed sensing problem is infeasible, returning LSQR. Result of LSQR. Really what I want to do is, instead of doing this, okay, I got it. Reconstructing without CS. If CS equals true and okay, now let's take a look at what we did. So far, we've just messed a bunch of stuff up. Okay, so I think I made a mistake a minute ago. Let's find out if I did or not. I don't want to show that image anymore. Because I think before we were doing psi and MFS. Nope, we were just doing MFS. Okay. And that, of course, is way way larger than the bound. Now, why would this problem be infeasible? Like, we knew the noise bound, right? And if it was overdetermined, why aren't we getting an excellent image out? Why are we getting these errors, these high frequency errors? And why all this noise? It's overdetermined. Aren't we supposed to get the right answer out? Well, there's noise, right? There's noise in the data values. But we took that into account, right? LSQR is just solving, minimizing the L2 norm of AX minus B, MFS minus B. The noise in the data we can take into account with the bounded constraint that we're using with compressed sensing. So why is compressed sensing not being used? Why is the system, like the overdetermined system, returning such a terrible result without letting us take advantage of the compressed sensing objective function? The reason is because of the sensitivity maps. So MFS is overdetermined. Well, it's full rank and it's tall and skinny. So the linear system MFS x minus b, or MFS x equals b, is overdetermined. And indeed, there's no solution to that linear system. Is there? No, there's only one solution, this solution. The issue comes down to the sensitivity maps. We say we have these excellent sensitivity maps that were determined by Pisco, and they're really good sensitivity maps, don't get me wrong, but they're wrong, they're incorrect. We know they're incorrect. Primarily, we know they're incorrect because there's really no such thing as a sensitivity map. Like, how do we possibly know it's correct? If it were correct, then we can numerically solve for the sensitivity maps using numerical electromagnetics, taking into account the coupled coils. But as soon as you put a body in there, that so-called loads the coils. And so changing magnetic fields in the changing electric currents in the coils changes magnetic fields in their sensitivity region, which causes eddy currents in the body themselves, which creates opposing magnetic fields. All of this is dynamic. So it's an approximation to say that there are sensitivity maps. It's obviously a very reasonable approximation. But we have this overdetermined linear system, and we know that, like, the true information, the information that we actually have in our matrix that isn't erroneous sensitivities, is much less than the information contained in the matrix of sensitivity maps. So what to do? Everything I just said is a hypothesis. Where's in samples? Sample fraction. Let's reduce this to 0.1. percent. This is going to be a significantly reduced by 30%, because we went from 10% sampling to 30% sampling. Okay, those are far fewer samples. Great, about 30% less samples. Still have the fully sampled center region. Is that overdetermined? Bound is 1 times 10 to the negative 6. This is 3 times 10 to the negative 2. So that wasn't enough. What I just did is reduce the number of outputs. I reduced the number of rows of MFS. There's 6,554 outputs. To MFS, to the matrix MFS, there are 6,005. No, there's that times the number of coils. Oh, right. 52,000. There's 65,556 inputs. So this is actually a short and fat matrix now. So still, it's underdetermined now. There are an infinite number of possibilities. But even though the system is underdetermined, it doesn't necessarily mean that it's feasible. None of those possibilities, apparently, satisfy this bound. Boy, oh boy. Okay. I think the answer is going to come from coil compression. I'm going to go back to the old sample mask. These S maps, what are they? 256 by 256 by 8. Okay. We have to decide the N compression, N compressed. So we're going to start out with N coils and we're going to compress it down to N compressed. S maps equals reshape S maps, S image, and coils. S image is equal to size, S maps, 1, 2, and coils is equal to size, S maps, 3. Okay, now we're going to do the SVD. I never remember in MATLAB, is it SVD or SVDC? SVD, okay. S maps, we're going to do the economical version. I don't even think we need V. Out is equal to U, 1, 2, and compressed times S from 1, 2, and compressed, 1, 2, and compressed. This I don't think is going to work, but we're going to see. Too many input arguments. Input must be two-dimensional. What is it? Oh. Okay. Those are the compressed sensitivity maps. Now we only have 5 of them. Okay. Okay. I think that's coil compression. Shang. Tao, by the way, very nice guy. Okay. Well, that was easy. Let's compress these coils. They look pretty similar, don't they? Oh, you know what? That's totally wrong. Because I have to compress the data as well. Right now, we've got too much data. How do you do that? So we have MFSX is equal to B. MFS is approximately equal to, well, let's see, S is approximately equal to U lambda. There's too many S's. S's. We need to read the paper. Here he's doing whitening. Good to know that that happens here. Okay, so the thing with whitening is that, okay, the noise is now independently, identically distributed, but the signal's been altered as well. And I find a new set of coils with data vectors, right? So they've whitened the data, so I don't understand that. In this work, we are only interested in data-based coil compression that does not assume explicit knowledge of the coil sensitivities. Previous studies, oh, this is one that I was doing, can be found in data-based coil compression. What is that? 14. So he doesn't, okay. Compute an inverse Fourier transform the case-based multi-coil data along the readout direction. Okay. At each X location, construct a data matrix X sub X, which each row consists of all the data from an individual original coil. Often just ACS data are sufficient. That's interesting. This is the auto-calibration region. Perform the SVD. Take the first M rows of UX to form an initial compression matrix. Oh, this gets complicated. What is this 14? Software channel compression technique. Maybe this is the paper I was looking at. Can I get it here? Find the input data set of PCA. The set data set is composed of n vectors. I'm starting to think I might just figure this out if I think about it instead of read it. I have to leave in 15 minutes. The idea is that we're relatively certain with these. Where are the compressed coils? Before A and B and after. So this is after coil compression. Okay, so we're confident in like a small number of these coil sensitivity maps. The rest, though, are noise. I have an idea. Is it just this? This is, can I do that? That's what I want to do. In Python, you'd use -1 or something. Okay, what if you do this? Yeah, this is what I want. Okay. So we don't, oh, this is fine. Okay. This is totally wrong. Okay, so the idea is that since we know that many of the principal components of the coils are just noise, we could take that noise away and hopefully end up with a better conditioned system. What about B? That's a helpful picture. All right, I'm gonna have to do this, like, do some reading outside of streams. I'll be better prepared to implement this. But at least now we're not. How much do I have to reduce the sample pattern in order to get an actually feasible problem? This compressed doesn't exist. .02. So something's still bound. Now I'm starting to doubt myself and thinking, yeah, see, here's the NB. It's because the noise variance is 1 times 10 to the negative 11. It's just super hard to get that up to a reasonable number. There's this abstract parameter-free parallel imaging and compressed sensing. And sure enough, it presents the problem that we're trying to solve, right? Auto-tuned variant of your SPIRiT. Three experiments were performed, and the first 20 fully sampled 3D fast-spin echo knee datasets acquired at 3T were downloaded from mridata.org. For each, when was this published? I wish it told me when it was published there. Answer is 2018. Okay, that's what? 7 years ago? Nine central slices were averaged to serve as a noise-free ground truth. And then noise was added. But how much noise was added? So in this problem, it's all simulation because they added noise themselves. And if you had enough noise For noise of sigma equal to 0.0128, yeah, okay. If you make this bound large enough, then it works, as we've seen. They added a bunch of noise, more than we're seeing in our data. We changed some code today. This is what we've changed over the last few days. So that's why this works. Because they added a lot of noise in order to make this problem feasible. And why that much noise? Well, they don't say. These are very good researchers. This is Tamir's work. But this never got published as a paper. So I'm wondering if that's a reasonable amount of noise, because either that's a reasonable amount of noise and we're estimating the noise incorrectly, or that's an unreasonable amount of noise. And they don't say here that they validated that much noise. This is us adding in compressed sensing into this code. We're going to check this in. Can't see the bottom of this window. No, we're not going to check that in. We're going back to a reasonable undersampling rate, 0.3. And so this should give us a warning. Yep, the compressed sensing problem is infeasible, reconstructing without compressed sensing. And right now, that just gives us the least squares result, which that's what that is. Part of the reason why there's so much high frequency noise, by the way, is because the sampling pattern is variable density with more samples in the middle, less on the edges of K-space. So, we have less information at the outsides of K-space. Good with all the rest. We're just going to get rid of this coil compression thing. Maybe that won't be the answer. Okay. And with that, we're going to end this stream. Hopefully next time, we'll either know how to make this work or know that it doesn't work. I'll see everyone later.